Thank you for all coming. As I said before, we're very honoured to have our speaker here to come and present to us today. There are major differences in the approach taken to seismic design in different regions around the world. As part of its focus on tall building design, the CTBUH has put together a working group to develop a guide on seismic design. The objective of this guide is to set out best practice for the seismic design of high-rise buildings for use in any seismic region in the world. The report has recently been released in a draft format, and our authors are currently conducting a world tour to present the guide's recommendations. To present to us today, we have one of the guide's authors, Dr. Andrew Whittaker. Dr. Whittaker is Professor in the Department of Civil, Structural and Environmental Engineering at the University of Buffalo. He started his career with Conor Wagner in Australia and has been based at various universities in the United States since then, including roles for the Pacific Earthquake Engineering Research Centre and Earthquake Engineering Research Centre. He has extensive experience in earthquake engineering and is well qualified to present the recommendations for the guide. Can you please welcome Andrew Whittaker.
Thank you. Thank you, Brett, and it's a pleasure to be back in Brisbane. This is the second time I've visited Brisbane in my entire life. So, although I was born and raised in Melbourne, I rarely made it north of Sydney. As Brett indicated, I'm here to talk with you today about the seismic design of high-rise buildings, and make this presentation on behalf of three folk, myself, and colleagues Michael Wilford, who runs the Advanced Technology Group for Arup in London, and Ron Klemenchik, who is the president of Magnus and Klemenchik Associates in Seattle, Washington. The Seismic Design Working Group of the Council was formed in early 2007, and it was formed in part in response to concerns that folks had about the design of tall buildings and compliance with codes of practice, recognising that codes of practice, principally the US codes of practice, weren't written for tall buildings, rather they were written for low and medium-rise buildings. And yet we were being forced as consultants to comply with inappropriate rules leading to potentially unsafe structures. So the Seismic Working Group was formed in early 2007. It's tasked with drafting best practice, international best practice recommendations for the seismic design of high-rise buildings, where we've tagged high-rise here as buildings of 50 metres in height and greater. And we published a draft of this document in early 2008. That draft was distributed around the world for review. We received comments from many countries around the world, including here in Australia. In April 2008, we've gone through an exercise of updating the document, and we will publish our final recommendations probably in late August. And the recommendations will be available on the Council's website. The specific goals given to our working group are listed here on the slide. The first was to review international best practice, because this was to be an international document, or a document for international use. We wanted to respect traditions and approaches around the world where possible. And we knew of performance-based guidance that was available in Japan and in China and in the United States. We wanted to identify shortcomings in existing standards with respect to high-rise buildings, and I've listed here three documents that have been cited for use in the design of tall buildings. Perhaps the most widely cited is the 1997 Uniform Building Code, which appears, well, I should say it's incorporated by reference in many codes around the world, from Southeast Asia through areas in the former Soviet Union, through into Europe. And this standard was written for low and medium-rise buildings, so we were running into problems when trying to apply the Uniform Building Code to the design of tall and super tall buildings. And last but not least, we were asked to draft appropriate procedures for analysis and design across all regions of seismic hazard in all regions of the world, which is no simple task. As we surveyed international practice, we learned that practice varies widely, from here in Australia through Southeast Asia, through Europe, indeed through Africa, and through North America. And there were no consistent performance objectives. So if you as Australian consultants wanted to practice somewhere in Southeast Asia, you would have to change gears in terms of what you're designing for. Often we design for what we describe as life safety, preventing substantial loss of life through design events. Well, that might have been appropriate here in Australia, it might have been appropriate in North America, but folks in other parts of the world were doing something substantially different. In some cases, there were no performance objectives. There were rules that said, just do this, with no understanding of what you were going to get at the end of the day. Importantly, the reliability of the resultant designs, and this is a bullet item here, was unknown. That is to say, we follow some prescriptive procedures, but at the end of the day, you didn't really know what they delivered. So this was a real concern. I've organised some of the discussion on international practice and what I've described, what I've used here as headings: traditional practice, emerging practice, and best practice. And I'm going to start by talking a little about the 1997 Uniform Building Code and its derivatives, in the large part because it is cited around the world. And I think it certainly was incorporated by reference in the Australian Earthquake Loading Code, at least in the last cycle. Now, the Uniform Building Code permits a large number of seismic framing systems. And I think at last count, in the 1997 Uniform Building Code, the count was in the high 60s. So there are 60 types of framing systems that one could employ in regions of moderate and high seismic hazard. Unfortunately, none were appropriate for high-rise buildings. The Uniform Building Code spelt out minimum lateral seismic forces. And when we characterise earthquake shaking for the purpose of design, we typically represent those earthquake shaking effects as horizontal forces. And the Uniform Building Code spelled out minimum lateral forces. Again, perhaps appropriate for low and medium rise buildings, certainly inappropriate for tall and super tall buildings. There was a laundry list of prescriptive rules that one had to follow. And these rules were developed, again, for low and medium rise construction using, in some cases, procedures and methodologies presented first in the 1950s, again for low and medium rise buildings on the west coast of the United States. The Uniform Building Code presented what I'll describe as single level design, where you design for this performance level of life safety for design basis earthquake shaking. In Australia, your design basis is a response spectrum with a 10% probability of exceedance in 50 years. We use something a little different in the United States, but they're not too dissimilar. And importantly, with our traditional practice, there is no performance check. You don't cycle back through the design at the end of the day to ensure that you're delivering the performance that's intended, in part because our procedures are sort of implied and not explicit. To provide a little more information on the Uniform Building Code, it's a document that's based on the CTBUH Blue Book. Now, CTBUH stands for the Structural Engineers Association of California, and since the late 1950s, CTBUH has produced design guidance, and for many years, only CTBUH was developing seismic regulations for use in the United States. So this was the book that folks would turn to for the state of art in earthquake engineering. But the Blue Book was based on US West Coast practice. It was written by West Coast engineers for West Coast applications, and about 99% of the building inventory on the West Coast is of about 4 stories and less. So that was the focus of design practice. When the CTBUH Blue Book was published first in 1959, there were 4 framing systems. Nowadays there are 78, but the 78 are all derived from the 4. In the first version of the Blue Book, there were 3 performance objectives with a single level check. So there was an expectation that your structure would suffer no damage in what they described as frequent shaking, frequent earthquake shaking, perhaps shaking you would see once every 10 or 15 years. That the structure would be quite life safe. There would be no substantial loss of life in rare earthquake shaking, perhaps shaking that might be seen every 100 years or 200 years, and then there'd be no collapse in the event of a very rare earthquake. So 3 performance objectives, yet there was only one single level check, and this was life safety in a rare earthquake. There was no check of the other performance objectives. So this was a significant impediment, in my opinion, to design practice, but it was indeed the practice of the day. The CTBUH Blue Book was written around force-based design. We're all familiar with force-based design, but this is problematic in that we expect our framing systems to suffer significant damage in our rare earthquake shaking. So we're designing for significant damage in rare earthquake shaking, yet we're using linear procedures and force-based design. There's a big disconnect here. So there's really no opportunity to check performance if you're using force-based procedures. Now, I'm not sure how many in the audience are familiar with seismic design practice, so I've got a slide here that's intended to illustrate the process, and so if you're familiar with seismic design practice, please bear with me. But this is US practice, and practice here is not too different. If we use this framing system, the 3-story frame, as an example, we go through an exercise of computing a design base shear V. That's the shear at the base of the structure here, and that design base shear is the product of a spectral acceleration, which is a representation of the earthquake shaking. W is the reactive weight of the building, and then this factor R is a response modification factor. So we go through a whole lot of busy work to compute the elastic demands on our framing system for our design event, and then we divide those demands by this response reduction factor, which typically takes on a value of between 4 and 8. Once we have computed this design base shear, we then distribute that force over the height of the structure using a first mode profile, which often takes the form of an inverted triangle. Then we take these reduced elastic forces, impose them on an elastic model of our building frame, and go ahead and design our structure. We assume that this process leads to a structure that's able to deliver life safety in the design shaking consistent with this spectral acceleration. It's an unproven and potentially unreliable process. But this is traditional practice. Now, the latest version of, quote, traditional practice in the United States is the 2003 CTBUH Recommended Provisions, and you can download this from a FEMA website in the United States. There are, at this point in time, 78 acceptable seismic framing systems. And if you look at regions of moderate to high seismicity, there are limits set on the height of nearly all framing, or most framing systems. If you're designing a building with reinforced concrete bearing walls, where the walls resist most of the gravity load in the structure, you can't build a structure higher than 49 metres. If you're using steel braced frames, again, there's a limit of 49 metres. If you construct a framing system that makes use of reinforced concrete or steel moment resisting frames, there's no height limit. And if you use a dual system, which is simply put a stiff primary framing system with a more flexible moment frame or backup system, there's no height limit. And the problem here, of course, is that steel moment frames and dual systems aren't really appropriate for very tall buildings. These are not framing systems you would use in 60, 70, 100-story buildings. I should point out that when we talk about steel moment frames in the reinforced concrete and steel moment frames in the United States, these moment frames don't correspond to tubular construction, which is one type of framing system used in tall buildings. So if we look at efficient framing systems in tall buildings, I've listed four types of framing systems here. We note that none of these are permitted per codes, standards and guidelines in any part of the world. So if you wanted to make use of a framing system with a reinforced concrete core and some outriggers to engage the perimeter columns, best of luck, you're not going to find that as a permissible framing system in any code, standard or guideline in the world. So suddenly you run into a problem with your regulator. So how does the building official check your work if you're using a framing system that's not allowed? So, and we ran into this problem on a number of occasions, and that was in part the motivation to write these recommendations. And I'll just note that there's really no technical basis to set aside these four framing systems for use in tall buildings, for use in seismic, for seismic resistance in tall buildings. None whatsoever. So with high-rise buildings, we see some significant differences in terms of response to low-rise buildings. The design procedure that I introduced a few moments ago that represents traditional practice, where you compute a base shear and then you distribute that base shear over the height of the building using a first mode profile. It might be appropriate for 2, 3, 4, 5-story buildings where one mode of response controls both the base shear and the overturning. But in tall buildings, we see that there are multiple modes of response that are critical to the base shear and critical to the overturning moment. One will often find that the first mode response will drive the overturning moment, which would influence the design of the core, the flexure, yet it's the second or third mode that might produce the maximum shears, which would influence the shear resistance of the core, for instance. So our traditional procedures, our first mode procedures, they are inappropriate for tall buildings where multiple modes control the seismic response. For seismic design of common low and medium rise framing systems, we tend to keep the gravity stresses in critical elements relatively low. And we do that because we have improved rotation capacity in elements with low axial force. But clearly we seek to develop high gravity stresses in cores and columns in high-rise buildings for economical reasons. So you try and drive the size of your core down to the degree possible. So you end up with very high gravity stresses. So this is kind of inconsistent with design practice for low and medium-rise buildings. If one was to use a traditional approach to designing high-rise buildings, namely computer-based shear by analysis of your structure and the use of a response modification factor, what value of R do you use for these framing systems that are widely used in tall buildings? Is a single value of R appropriate? Should you use a different response reduction factor for modes 1 and modes 3? It's impossible to know unless you do a case-by-case analysis, in which case you can probably go ahead and perform a performance-based design. Also, for high-rise buildings, wind loadings can often control. This is not the case for low and medium-rise buildings. So there's a big disconnect between low-rise buildings and high-rise buildings in terms of seismic design. So with the stage set, let me move on and talk about emerging practice in the United States, and then I'll talk a little about best practice in Japan and China. We are in the process of developing the second generation of tools for performance-based earthquake engineering. That said, the Gen 2 tools are under development, and there's building off the Generation 1 procedures that were developed in the mid to late 1990s. And it's the Generation 1 procedures that are used to backstop the Council's recommendations. Performance-based seismic design enables the engineer of record or the architect, the design team, to identify performance objectives. And there are strong recommendations that multiple objectives be identified. So instead of using the single level check that we've used to date or used in the past, there is significant attention paid to selecting multiple performance objectives, which might be no damage in frequent earthquakes and no collapse in a very rare earthquake, but there's an expectation that you check for that explicitly, so you deliver on the performance statements. Performance-based seismic design enables significant design freedom. So you pick the framing system, but then there's a burden on the engineer of record to demonstrate that the intended performance is achieved. And there's some significant design burden. You have to move away from the traditional prescriptive rules that we find in our codes of practice. And I've listed some of the design burdens here, namely one has to undertake detailed seismic hazard computations, often undertake nonlinear dynamic analysis. We use component checking procedures based on the deformations, not forces, and there's a significant attention paid to first principles mechanics that takes us all back to our university days. And a key part of performance-based seismic design is peer review. Peer review 20 years ago in the United States was kind of frowned upon. Engineers of record really didn't much care for someone to be looking over their shoulder during the design process. I'd say that in the past 20 years, attitudes have changed. And in that peer review is now looked upon as a kind of a partnering exercise. Gives you a fresh set of eyes looking at what you're doing. And one could argue that peer review is appropriate for traditional practice. I think it's become mandatory for use with performance-based design. So let me talk just briefly about the Generation 1 performance-based earthquake engineering procedures. I've listed some resource documents here, FEMA 273 and FEMA 356, published in 1997 and in 2000 respectively, and more recently ASCE 41. ASCE is the American Society for Civil Engineers. They publish standards. This is Standard 41. It was published in 2006. And you can download FEMA 356 from the FEMA website, and you can purchase ASCE 41 from ASCE. But with our Generation 1 performance-based earthquake engineering, we identified multiple performance levels. And the performance levels are shown here in a cartoon form, ranging from operational all the way through to the point of incipient collapse. Now, in years past, we've focused on this third performance level, namely life safety, and really we're looking at building performance here as it's associated with no significant loss of life. So if you have 200 occupants in a building and 2 are killed during an earthquake, in my opinion, that would be life-safe performance. We don't live in a risk-free world, so people will die in earthquakes. We just don't want wholesale loss of life that might be associated with a building collapse. If I move to the left, operational is kind of self-explanatory, and it differs from immediate occupancy here, only in the sense that if the building is operational, you require gas, power, and perhaps and other utilities. And the provision of off-site utilities is well, it's problematic. Well, providing off-site power and the like is problematic after major earthquakes. You typically see, especially on the west coast of the United States, that power, gas and water are lost for a significant period of time after major events. So if you want operational performance, then you have to provide on-site power, on-site water, on-site gas and so on. And this last performance objective, collapse prevention, again is self-explanatory. Just to explain perhaps in a cartoon form emerging practice in the United States, I plotted here base shear, or essentially resistance of the building versus structural displacement, perhaps the displacement at the roof of the building, or put differently, earthquake intensity. So from minor level of earthquake shaking, we might look to operational performance. For an increased level of earthquake shaking, we might look to immediate occupancy type performance. As we increase the shaking a little more, we get to the third performance level of life safety. Here we have the performance level of collapse prevention, and as we move beyond collapse prevention, we have structural collapse. But these are the four performance levels that you'll find identified in the documents referenced earlier. Now, with performance-based earthquake engineering, the Generation 1 tools, we seek to match performance level and hazard level. We do this explicitly. If you think back to the discussion on the CTBUH Blue Book, we said we don't want damage in a frequent earthquake. And whilst damage is fairly easy to understand, frequent wasn't defined. When we talked about life safety in a rare earthquake, well, there are probably 60-odd folks in the room, and I could ask each of you to define life safety, and I'm sure I'd, at the end of the day, have 70 answers. And also rare earthquake shaking wasn't defined. Now we've actually spelled out some performance levels and some hazard levels, so we're being a lot crisper about the whole process. So one might say that a standard design might make use of the operational performance level for earthquake shaking with an annual frequency of exceedance of 1 divided by 100. And then as we increase the return period on the earthquake shaking, we move from, say, frequent shaking to very rare earthquake shaking, perhaps shaking with a return period of about 1,000 years, we might accept damage that's associated with the performance level of collapse prevention. But we're now marrying performance and hazard, and we put the two together to form a performance objective. With our Generation 1 procedures in the documents cited a few moments ago, we provide nonlinear force displacement relationships to enable the engineer to build models of structural components. And in the Generation 1 procedures, there was substantial attention paid to what we describe as nonlinear static analysis. So it has many of the features of static analysis that you perform at this point in time, but it's incremented static analysis, whereby we would impose a first mode lateral profile on the building, and then in essence we'd push the building to the point of incipient collapse. And this is an approach that's appropriate for low and medium rise buildings where one mode of response controls the behaviour of the building, but it's inappropriate for tall buildings where 2 or 3 modes in each direction might contribute to the response. Importantly, as we introduced nonlinear static analysis to the United States in the mid-1990s, we recognised these limitations. But we were moving from a profession that was comfortable with equivalent static analysis. We wanted to get them to nonlinear dynamic analysis, and nonlinear static analysis was the stepping stone. So the Generation 1 procedures are crafted around nonlinear static analysis, but with mention of nonlinear dynamic analysis. The Generation 2 procedures that we're developing at this point in time as part of the ATC 58 project have moved on from nonlinear static analysis to nonlinear response history or nonlinear dynamic analysis. So now we've talked about traditional design practice, principally in the United States. We've talked about emerging practice in the United States. We talk about best practice in Japan and China, where I'm sure some of you practice. Performance-based earthquake engineering has been used in Japan and China for a significant number of years. So really they've led the world in implementing performance-based earthquake engineering. And I'll just note that the Japanese have been making use of performance-based design since 1981. Now, it's a little different from what we're using now in the United States, but to give the Japanese credit, they've been thinking about these performance issues for more than 25 years. Performance-based earthquake engineering has been mandatory in Japan for many years for buildings exceeding 60 metres in height. They recognised that their codes of practice weren't suitable for tall buildings, so they have required performance-based earthquake engineering of tall buildings for many years, and again they defined a tall building as 60 metres in height. And the corresponding limit in China depends upon the hazard and the seismic hazard and the structural form, but it's of the order of 50 to 60 metres. Performance-based earthquake engineering in Japan and China enables the engineer to use non-traditional framing systems and materials. They typically require multiple performance checks. They've used nonlinear response history analysis, again, for many years, and component checking is not really deformation-based, it's ductility-based. So, and the two are related. So in Japan, they make use of two performance objectives, and the performance objectives are tied to levels of what we call peak ground velocity, which is a ground motion marker that's really only used in Japan to my knowledge. But for all intents and purposes, you can say their level 1 check is associated with a peak ground acceleration of 0.25 g, and their level 2 check is associated with a peak ground acceleration of 0.5 g. And you can see for each of these levels that there are different performance requirements. So for level 1, we expect elastic response in the structure, i.e. no damage, and for the level 2 earthquake shaking, there's an expectation that this story ductility factor be less than 2. Now, a ductility ratio is nothing more than the ratio of maximum displacement to yield displacement. So maximum inelastic displacement to the yield displacement. So with a story ductility factor of 2, the degree of damage is relatively modest. So long story short, the Japanese design stiff and strong buildings. If you were to compare a medium rise or a high rise building in Japan with its counterpart in the United States, a Japanese building is going to be a lot stronger and a lot stiffer. And Japanese practice has required expert panel peer review since 1981. In China, they make use of 3, not 2, performance objectives, again tied to hazard. In the Chinese practice, we look at shaking with return periods of 50 years, 475 years, and 2,475 years. And listed here on the slide are the corresponding performances, namely elastic response, repairable damage, and no collapse. Again, there's a requirement in China for expert panel peer review. So the Japanese and the Chinese are way out ahead of us in the United States in terms of implementing appropriate procedures for the design of tall and super tall buildings. So with that background, let me move on to the recommendations in the Council's document. And shown on the left-hand side of the slide is a mock-up of the cover. And I think if you visit the Council's website, you'll see this draft version of the recommendations, which will be finalised later this month now. And listed on the right-hand side of the slide are the chapter headings. Of interest here might be Appendix B, which is performance assessment or seismic performance assessment in regions of low seismic hazard. And quite frankly, we've grappled with this a little, and what you'll see in the final version of the recommendations is a little different from what's in the draft version. But if you're looking to design a building, a tall building, say here in Australia, or say in Abu Dhabi or Doha, Qatar, you might make use of Appendix B in this document. So after we had reviewed international practice, we settled on some minimum design objectives for our recommendations, and we required a service level assessment and a collapse level assessment. And the service level assessment really requires no damage in the structural framing system or damage to the non-structural components for earthquake shaking with a return period of the order of 50 years. So this is the frequent earthquake described earlier but now quantified. For a much longer return period, we undertake a collapse level assessment, and the expectation here that we have a high probability that there be no collapse for spectral demands with a return period of about 2,500 years. And you might ask, well, where does 2,475 come from? It's a 2% probability of exceedance in 50 years. And in order to achieve this performance of no collapse, we limit deformations for ductile actions and we limit forces for non-ductile actions, and I'll explain this a little later on. We provide procedures for seismic hazard analysis, and we require that the engineer of record undertake a formal seismic hazard assessment, and this is appropriate for a tall or super tall building. We require the development of 3D nonlinear building models for regions of moderate and high seismic hazard, and we provide some counsel on what has to be included in that building model. We require that the engineer of record perform nonlinear response history or dynamic analysis, and this is a requirement based upon our understanding of the response of tall buildings under unimodal type load profiles, in that you can't hope to predict the behaviour of a tall building subjected to earthquake shaking using simple static procedures. We require an assessment of results in terms of building deformations. This would be more of a global check, and then we check component deformations for ductile actions and component forces for non-ductile actions. And a key shortcoming of the document, and you'll pick this up as you read through it, is that we link system response to component response. Our component deformations are, the acceptance criteria, let me say, are spelt out in terms of performance levels identified earlier. So if you're looking at rotations in a beam, for argument's sake, then we have acceptance criteria for those deformations for the performance objectives of immediate occupancy, life safety and collapse prevention. Increasing levels of damage, increasing values of that plastic hinge rotation. But one goes through this performance check component by component, so quite similar to traditional practice. But at the end of the day, we link system response to component response. So let's say you have 100 beams in a building, to pick a number, and 99 of those beams have performance that would be consistent with life safety. One of those beams has performance, rotation, associated with collapse prevention. Then the system performance is linked to component performance, and we would say that that building is in the collapse prevention performance level. This is a major shortcoming, and we don't have, or we didn't have when we wrote the FEMA 273 document, a simple way of linking component behaviour to system behaviour. But we felt that we had to implement the procedures at the component level, in that this is what engineers are familiar with. So it's a shortcoming of the process. We require the engineer of record to develop a seismic design basis document, and I suspect that this is pretty standard fare